start part B of module 1, efficient polynomial evaluation. In this part, I will give you 3 videos, not 4. The reason is some other videos relatively longer, so I have to control within 60 minutes. So total 3, not 4. So sometimes 3 videos, sometimes 4 videos. That's pretty normal. All right, so let's start. First, let's look at our first computing problem example in this class. So what's that? It is a problem we are quite familiar with. Evaluate a polynomial. So let's look at the problem first. Given a polynomial in this expression, p of x equals this standard formula. Here, a0, a1 through an, the coefficients. So we can treat them as constants. So we do not frequently change them, because when we change, we switch to a different polynomial. The definition, when you define a polynomial, these coefficients must be fixed. Okay? All right. Then x is treated as a variable. So we can change its value, pretty much as you want. Okay? Now the question. The problem we need to solve. How to evaluate p of x efficiently. This is an important keyword. What do you mean efficiently, right? It's pretty vague. How do you interpret this term efficiently? We will see that, because it is an important concept for this class. We will have a lot of discussion on it. Analysis. First question. To evaluate a polynomial, I believe every one of you can do it easily, right? If I ask you to write a program to evaluate a polynomial, can you do it? I believe everyone in this class can do it easily. But the question is this: efficiently. You may not know your evaluation is efficient or not, right? You may not know it. So that's the reason we do it in this class. We will see it. We will find the answer in this class. Okay. All right. Algorithm. From part A, I hope you have some understanding, basic understanding of the algorithm. The question, do we really need some unusual algorithm to solve this problem? The usual one, so everyone knows that one, the one we're talking about, the usual one. But the question is, do we really need an unusual, some very special algorithm to solve this problem? That's the point. Okay. So let's, do more analysis. All right. We observe this polynomial only contains addition and multiplication operations. Simple fact, but we will have a lot of discussion on these two operations. Next question. How to measure efficiency. How to tell if an algorithm is efficient or not? That's a fundamental question in this class. Efficiency, how to measure it. Okay. All right. First, simple answer, we try. Can we use execution time to measure it? We write a program, we run it on a computer, then we clock it. We clock it. We have a way to calculate the execution time, right? Yeah, because in our programming language, we can find some special functions that tell us how to calculate the execution time. If we can find execution, can we use that to measure efficiency? Yes or not? The answer, you can use it to measure, but it's not a good measure. Execution time is not a good measure. Why? The reason is very simple. Think about it. When you run a program, what computer do you use? Do you use a powerful computer or low-end, very slow computer, right? Do you use a supercomputer or do you use a 10 years old computer, right? That will determine the execution time with big difference, right? So the reason it's not a good measure is this one not stable, right? Sometimes bigger, sometimes slower, depends on a lot of factors. We don't like that kind of measure, not stable. So we like to pick a stable measure. What do you mean stable? When you run it in different computers, using, different software, whatever environment you use, you can have the same, relatively more stable measure. That's what we need. Is it possible to get that? Yes. Here, let me point that out using number of additions and multiplications. Think about this. You count how many multiplications, how many additions do we need to calculate, to evaluate this polynomial? Does it rely on computer performance? No. On a slow computer or super fast computer, the same efficiency number. Stable, so that's why this one is a, pretty good one because it is stable. It is more stable, right? All right, so let's stop here in our efficiency discussion. All right, next, let's try it. Let's try to, solve it. First try, because at this point we do not have any new idea how to solve it efficiently. We only know one solution, the straightforward solution. That's the only one we know it. Yeah. So that's what. Let's start with this straightforward algorithm. So the one everyone knows how to do it. Okay. So I do not need to, waste my time describe it. All right. But when you do the evaluation, you need to do this kind of typical work. So what's that? Work on each term. So this is the general expression of one term. The k starting from 0, 1, and the last one is n. Okay? So n can represent from 0 through n. Very general expression. And when we evaluate one general term, we only do multiplications, right? We do not do addition. Single term, there is no addition. After we get the values for all the terms, we do additions to add them up. Okay, so that's our straightforward solution. All right, so now the question, when we use this method, the question, how fast it is. Okay. All right, before we continue here, let me give you the reference on the textbook. Section number and a page number. Here you can see, pretty late one, 6.5. Yep. So I do not start from the very beginning following the order of the textbook. Here I jump to chapter 6, section 5 first. The reason, there is some important reason I choose in this way. First, this is a very interesting example. It's simple, polynomial evaluation, how simple it is, right? But the solution is, extremely smart, And in my early classes, I like to impress you. So I pick this example. I try to impress you. Another reason, okay? But there is a third reason. Remember, we need to do our project 1 really fast for this short semester, 8-week short semester. We need to do our project number 1 very, very early. And this one, I can design a relatively simple project, but it can give you some strong impression on algorithm efficiency. So that's my intention. That's my design goal. Now, on Thursday, on our lecture Thursday, we will complete module 1. Yeah, because we spent part A, B, C, D, right? Monday, Tuesday, Wednesday, Thursday. 4 days, we will complete module 1. So at the end of module 1, I assign you project 1. Project 1 is this problem. This problem. I will give you the detailed description at the end of the Thursday's lecture. Okay. All right, so let's continue. Yeah. All right. The question is, is your algorithm efficient? The one we're talking about, right? This one, straightforward algorithm. Is that one efficient? Can we answer that question? May not be that easy. We need to do a lot of work. We need to, develop a lot of things before we can answer this question. Okay? All right. Next question. Are we satisfied with this solution? That's another question not easy to answer. I believe most of you will say, yes, we're satisfied, because we always evaluate in this way. So we're pretty, satisfied with this one. Okay? If we will see part C, we will see if you see a smart solution in part C, next lecture, then your answer will be different. Your answer will be different. Otherwise, why I talk about this problem, right? There is no reason I pick this problem. The reason I told you before I picked this problem, there is a smart solution. Surprisingly smart solution for it. We will see. Yeah. All right. Next. We like to know how bad it is. How bad it is. We need to do comparison, because when we compare a better one and a good one, how much is the difference? We want to see that part. Okay, and we will see it. in part C. Yeah. All right. Before we do it in part C, we need to do another important thing here. Find the performance number of this algorithm. Performance number. What's the performance number? Here, number of additions and the number of multiplication. That's the meaning of performance number. Okay, yeah, all right. So let's do it. Yeah. All right. This time we set our goal. Find the number of operations. Yeah. Number of operations. But we have two operations, addition and multiplication. They are different, two different operations. Can we add them up? One addition, you have one. One multiplication, you have another one. Can we add this 1 plus 1 equals 2? We cannot, right? Apple compare apple. Add one apple plus one apple, but you cannot one addition plus one multiplication. That's not the right way, right? Yeah. So we need to do something to improve it. Improve that kind of direct addition. Yeah. All right. We need to add some assumptions. Add some assumptions. How can you add assumptions? Here, let me give you the reason. Yeah. In problem solving, it is allowed to add reasonable assumptions. Because our goal, we want to solve that computing problem. To that end, we may need to set up our environment, right? We need to set up our computing environment. When we do that, we just make some reasonable assumptions. What do you mean reasonable assumptions, right? What do you mean reasonable assumptions? Yeah, here, let me describe a little bit. Yeah. The added assumptions should not alter our original problem significantly. Okay. You change a little bit, but still, you do not change the main properties of the original problem. Okay? Yeah. So your solution on slightly modify the problem can still reflect the, solution for the original problem. Okay? So that's the criteria we use for assumptions. Yeah. Here, let me make that first assumption. Each addition takes 1 unit of time. Can we do that? 1 unit. Here, I do not specify how much is that unit of time, right? Certain unit of time. Certain amount of time as 1 unit. That's okay, right? That's not too much change. Yeah. But here, let me describe this unit, time unit. Usually, based on the real world situation, okay? Yeah. We try to be more realistic when we make assumptions. Yeah. Certain number of nanoseconds in this category. Nanoseconds. I hope you have sense about nanoseconds. How big is 1 nanosecond? You know that, right? Here, let me just remind you, 1 nanosecond and s equals 10 to the -9th second s. In other words, 1 billionth of second. 1 billionth. That's small. Nanosecond, that's small. Okay. All right. Yeah. Second assumption. Each multiplication takes 10 units of time. 10 units of time. Okay. 10 to 1 ratio. The second assumption also pretty much reflects the real world situation. Not very precise, but pretty much in that relative comparison. Okay, yeah, comparable in like that. Okay, all right. But after, you can see after we make these two assumptions, then our discussion can be simplified a lot, right? We can do addition this time, right? Because we can calculate the number of units of execution time we use for this algorithm. We can calculate units of time, right? Yeah. Do conversion. Yeah. All right. Now we do the work. Do the work. Our first computing work job we need to do. Yeah. What's that? All right. So number of additions. Can you tell me when we evaluate this polynomial, how many additions do we need? Try yourself first. It's a simple answer, yeah, but I hope you can get it before I talk about the answer. All right. All right, so let me talk about the answer. All right. Here, we need to use a counting technique. Counting problem. You learn counting in discrete math, right? So there is a, chapter or section about counting problem. Okay, you have that background. Yeah. So here we need to use one of the counting techniques. Yeah. So what kind of counting technique? Yeah. Here I call it counting by reference. This technique. It's a simple counting technique, but very effective. So let me explain the idea here. So what do you mean counting by reference? Yeah. Here. The essence of the method is like this. Okay. All right. We discover one-to-one correspondence between two mathematical objects. Here, most important thing is this kind of one-to-one correspondence. When we have that, we can do the counting by reference easily. Okay, let me further explain this idea. Yeah. Because even you just look at the sentence, you may not get it. Yeah, let me explain a little more. Yeah, here, let me use this box to explain. Use this box as a diagram to explain the idea. Yeah. Suppose we have two mathematical objects here, very abstract, two mathematical objects. What kind of mathematical objects? Yeah. Based on your problem, we can define what are those two mathematical objects. Yeah. So we will see that using this example soon. Yeah. All right. Then we need to find one-to-one correspondence between these two objects. Yeah, that's most important thing we need to do using this counting by reference technique. Yeah. But why are we doing this way? Why are we doing this way? The reason is this simple. Yeah. The first object, relatively hard to count. Relatively hard to count. If you count it directly, we couldn't get it easily. Yeah. So later I will use this example to show. Yeah. But the second object much easier to count. Second object, it's a different object. But if we count the number of second object, very easy to count. But first one, second one, there is one-to-one correspondence. Then we do not count object 1 directly. Let's switch to object 2. Let's count object 2. After we get answer, that's the answer of number of object 1. How about that? How about that idea? Okay? Yeah. Pretty neat. Yeah. Let me use our example here to explain that idea. Okay? Here, I'm asking you to count the number of additions. Okay? Yeah. But additions corresponds to object 1. Yeah, because if we look at the formula, can you see the number of additions quickly? Some of you can, but I believe large number of you cannot. You get lost. How do I keep track of all the additions, right? Because here, dot, 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 you see a dot, dot, dot. You get lost because you cannot keep track of the part. We skip it in dot, 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 right? Yeah. So we have to recover that part, that missing part, dot, 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 okay? So that's why here in this example, addition, that's our object 1. Yeah. It's hard, so we want to switch to a different mathematical object. That one, much easier to count. Then we apply this counting by reference technique. What's the second one? Okay, here. Look at the subscript. A sub 1 subscript. Is that another mathematical object? So our object 2 subscript. Okay, subscript. Okay, you can see the first plus sign associated with first subscript, second plus sign associated with second subscript, and so on. The last plus sign associated with the last subscript, n. Okay, is that one-to-one correspondence? 1 plus sign corresponds to exactly 1 subscript. So we establish one-to-one correspondence between these 2 mathematical objects. After that, do you think it is much easier to count the number of subscripts here? Okay? Because in our one-to-one correspondence, we don't have any plus sign corresponds to a sub 0. We don't have that, right? So when we do the counting, we exclude a sub 0 term. Okay? Then the number of subscripts that have one-to-one correspondence with plus signs from 1 to dot, dot, dot through n. When you count the number of numbers here, will you get lost for the dot, dot, dot part? You will not, right? Because 1, 2, 3, the natural numbers in order, you won't get lost, right? Nobody will get lost for that dot, dot, dot part, missing part, okay? So we can comfortably get the answer. The total number is n. Counting number is n, okay? Then can we go back to the number of object 1, the number of additions? Also n. How about that? That's the counting by reference technique. And for this class, we will use this technique many, many times. Okay, all right. And then later in our exercise part, I will give you a few more examples to practice this counting by reference technique. Yeah. All right, so now we have the answer, n units of time, because one addition takes 1 unit of time. Okay, so then simple conversion, n units of time. All right, so that's the content for our B.1 video. All right, so let me stop here. Yeah.